You need something over there?
What? No, just good to go.
Yep.
All right. Let me see. All right. Good morning, Gumshoes. Today I'm here to share a case that landed on my desk not too long ago. You might say this is all the makings of a classic cloud mystery. It started like they always do, with a phone call. Major customer, real big account, reporting errors. Support tickets were piling up faster than coffee cups on an all-night stakeout. And then came the words that make every cloud detective's stomach drop. If this doesn't get canceled by the end of the quarter, we're canceling our contract. The customer's reports were vague. They kept saying, sometimes things spin for a few seconds, and then an error page pops up. But the issues were intermittent, with no clear pattern, and different users were all affected. On our end, everything looked fine. Health checks were green, traffic patterns were normal, and our application log showed no signs of trouble. In fact, every request was completed successfully. It was a classic mystery, a ghost in the network. Louder? Okay, yep. If everything seemed to be working, where were these requests going? Why couldn't we see what the customer was seeing? It was as if the requests were disappearing into a black hole. Today, we're going to solve the mystery. We'll meet the suspects, examine the evidence, and master the tools you'll need for a case like this. And I promise that by the end, you'll know how to map the territory, track down elusive bugs, and most importantly, prevent future cases from haunting you. Because if there's one thing I've learned in all my years of debugging, it's that the cloud may be someone else's network, but the detective work, that's all ours. First, let's talk about some of the greats. Sherlock Holmes famously said, as you eliminate the impossible, whatever remains, however improbable, must be the truth. In our cloud detective work, this translates to systematically eliminating components until we find the culprit. For example, if we see the same behavior, whether we go through the CDN or around it, we can remove the CDN from our suspects list. But like Holmes, we need to be methodical. No jumping to conclusions without evidence. Benoit Blanc tackles cases by breaking them down into fundamentals, means, motive, and opportunity. Let's map these to our cloud problems. Means, which component could technically cause the failure? Motive, which behaviors or situations would trigger the issue? And opportunity, which components live across the request path where the error happened? Finally, we have Columbo. His persistent questioning and just one more thing approach can be incredibly effective. In our world, this means diving deeper into assumptions and asking just one more time, are we sure there hasn't been a firewall change? All right, Gumshoes, every good detective knows you don't start an investigation without the right tools. Documentation, request flow diagrams, and runbooks are essential ingredients to solving a case. Every cloud detective needs solid documentation, because trust me, in cases like these, the devil is always in the details. First things first, we need to know what we're dealing with. And your architecture docs should help you understand service boundaries, where one team scope ends and another begins, network paths, where the route your requests should take, and integration points, where services meet and mistakes happen. Next, your request flow diagram. Think of this as your victim's timeline. Where do they go? Who do they talk to? And what should have happened at each step? Ideally, the request flow diagram shows the complete journey of a request, both upstream and downstream. Many teams meticulously document their downstream dependencies, databases, caches, backend services, but treat upstream components like a black box. This is a classic cloud mistake. A bug in your API gateway will break your user's experience just as thoroughly as a database failure. So document everything with equal care and precision. We need to know the latency expectations, timeout policies, and retry logic across your entire request path. Finally, the runbook. This is our go-to guide when things start getting messy. It should cover common problems, known resolution steps, and context for each system. A good runbook is like a case file. At the top, you've got your most wanted list, the common suspects that cause the most trouble. And for each one, you document the victim statements, say user reports timeout errors when uploading files, the evidence, load balancer logs show 504 errors, known associates, which systems are typically affected, and the usual solution, check CDN upload size limits. But here's the real trick. You want to organize it by what your victim reports and symptoms, not the root cause. Your 3 a.m. brain will thank you later. A bad example might be memory leak detection and resolution, while a better example would be 502 gateway errors. What you'll see, users reporting errors after midnight. Common causes, memory leaks in the processing service. Quick fix, restart processing nodes. Long-term fix, memory leaks tracked in Jira 133K. And always include team contacts, who to wake up at 3 a.m. Required permissions, because there's nothing worse than lacking access in a crisis. links to dashboards, aka your surveillance cameras, and links to past incidents, because criminals often return to the scene of the crime. Now, no detective goes to a crime scene without their forensic tools. And when it comes to the cloud, we've got some powerful options. First up, observability tools. Think of these like your magnifying glass, zooming in on the details to reveal what's slowing down or breaking requests as they travel through your system. These are best for understanding the full request flow and identifying bottlenecks. In a case like ours, these tools could reveal if a request is getting delayed or stuck at a specific component. Unfortunately, these are usually integrated at the application level, and sometimes trace information is missing at higher levels of the cloud network stack. Logs are like witness statements. They give us timestamps, error codes, request IDs, and client information. But just like in detective work, you need to know which logs to look at. System logs, network logs, load balancer logs, they all tell a different piece of the story. When combing through the logs, pay attention to patterns, reoccurring errors, suspicious gaps in activity, or specific times when issues spike. These can help pinpoint a problematic service or an unusual time of day. But remember, gumshoes, logs can lie by omission. Sometimes the most important clue is what's missing. Finally, there's nothing like seeing a user's perspective to bring clarity to a case. User journey recorders let us watch the crime from a user's point of view. Tools like Sentry, LogRocket, or FullStory record and replay user interactions on a website. They can be an invaluable source for clues because they often contain full network logs from the user's browser. When a request disappears or errors don't show up in our own logs, these tools can give us that missing perspective. Well, we see what the story as the user sees it, and that can be crucial to solving the case. Any good detective knows that a crime doesn't happen in a vacuum. There's a whole scene to examine, and in the cloud, a crime scene is vast, layered, and often underdocumented. Most people picture the path as simple, from user to cloud to app. But in reality, it's a complex web, a whole network of services with checkpoints, and each with its own quirks, configurations, and points of failure. So let's break down this crime scene, one step at a time. Because to solve this case, we need to understand the exact path each request could take. Let's meet our cast of characters, the usual suspects in any cloud caper. The DNS has a notorious reputation. Its job is to translate names to addresses, routing requests to the right place. But if the DNS isn't working correctly, your users will never find your application. Issues here can include propagation delays, misconfigurations, and cache problems. The old pro tip when dealing with any sort of DNS change is to drop your TTL settings down to about 5 minutes, 48 hours before a major DNS change, so you can quickly recover from any mistakes, and only bump it back up to 24 hours once you're confident the entire system is working, not just the DNS. Next, we have the CDN. These were originally built as large caching systems, storing content close to users by placing copies in key locations worldwide. In recent years, their role has grown. Now they run code directly at the edge, using services like Cloudflare Workers or Lambda. Common cases involving the CDN include cache poisoning, when stale or incorrect content gets stored and served, regional routing mishaps, when traffic gets sent to a distant edge node instead of a nearby one, configuration drift between edge nodes, what works in one region fails in another, and edge function timeouts, because code running at the edge typically has stricter limits than your application. A pro tip for CDN investigators, always check the cache control headers. I've seen many a case where a misconfigured cache header led to content being cached when it shouldn't be, or worse, not cached when it should be. Once any company reaches a certain size, incentives push them to install a WAF, or Web Application Firewall, in front of all web traffic. WAFs are good at filtering requests, enforcing rules, detecting bots, and limiting rates. But sometimes, legitimate requests get caught in its net. Rate limits and low-quality IP filters are common sources of problems that might originate in the WAF. So keep an eye out if you have a particular feature that triggers a flurry of web requests, or if your customers like to use a VPN to access your website. Our load balancers are responsible for distributing requests across multiple services to keep things running smoothly. But when misconfigured, they can cause an uneven distribution, overloading some services while others are happy. Misconfigured timeouts or sticky sessions are other common problems. Your application server might be completing a request, but the user still gets an error if the load balancer got sick of waiting and closes the connection before the app was done. Next, we have API gateways, including request routing, rate limiting, and sometimes authentication. Common issues that crop up here are routing mismatches or configuration drift, sending traffic to the wrong service. Authentication issues are also common at this layer if the API gateway and client aren't configured correctly. Kubernetes Ingress is another tool for routing external traffic to services running inside your Kubernetes cluster. It acts as a gatekeeper, managing how traffic flows to your cluster and directing it to the appropriate pod based on routing rules. A common issue with Ingress is misconfigured routing rules. If these rules don't align perfectly with your app's expectations, requests can get lost, redirected, or blocked entirely. For example, a typo in a host rule might send traffic intended for your service to a dead endpoint, leading to 404 errors. Another frequent challenge is dealing with the behaviors of different flavors of Ingress controller. Each one has its quirks, so find out which one your company uses because you can't always trust the default documentation. Firewalls block or allow traffic based on rules, port filtering, and network segmentation. If no requests are making it to your application server, it's possible your firewall isn't allowing any traffic from outside the network. Unfortunately, I found they don't log much. They don't explain much, they just block. Blocked ports or rule conflicts are common reasons that traffic might be getting dropped before it can access your internal network. Finally, we have the application servers. I'm sure you're already imagining why this is on the suspects list, so I won't bore you with its full rap sheet. Every one of these components was built by engineers like us. Each service, whether it's a load balancer, an API gateway, or a CDN, is just another software solution. And each one has logs, metrics, and configurations. We can debug these just like any other service. It's easy to get intimidated by cloud infrastructure, to think of it as some mystical black box, but at the end of the day, we're dealing with code, written by developers like us. Understanding ownership is crucial too. If we identify an issue and say, the load balancer, we need to know which team manages it. At some point, we need to know who to call when we need backup. And just like in old-fashioned detective work, building relationships is crucial. While detectives read fingerprints and tire tracks for clues, cloud detectives need to master their own form of evidence analysis. Fortunately, most cloud services speak a common language, HTTP. Status codes, response headers, and response bodies are fingerprints. They tell us who last touched a request and what happened along the way. But there's a catch. Just like with forensic evidence, we need to know how to read these clues correctly. Let's start with our 400-level status codes. These are your client-side errors, but don't let that fool you. The client isn't always to blame. 400, bad request. Some common causes include request headers being too large, so check your cookies, or malformed request values. When you find evidence of a 400, some common suspects include firewall rules, load balancer limits, or proxies. 401, unauthorized. A 401 usually means that authentication details are missing or incorrect. A common suspect here is the API gateway, because these are often coupled to authentication logic. But also make sure to check if headers are being preserved across your proxy chain. If something upstream isn't forwarding your authorization or cookie headers, then downstream services won't be able to authenticate the request. 418, I'm a teapot. Yes, this is real, and no, you're probably not trying to brew coffee in a teapot. In modern systems, web application firewalls have adopted this classic April Fool's Day joke to use as a unique signal to help cloud detectives like us know when we should be taking a closer look at the WAF configurations. 429, too many requests. Our rate limiting friend. If you see a 429, it means some component, usually an API gateway or a WAF, is putting the brakes on your traffic. Double check rate limit configurations and traffic patterns. If you've got a bursty feature, that could be the cause. 500, internal service error. This is the all-purpose something went wrong code. 9 times out of 10, when you see a 500, check your own application first. Most of the usual cloud suspects are well-behaved and robust, so they typically don't break in unexpected ways. But you can never say never. 502, bad gateway. This usually means something is misconfigured in your request chain. The most common issue I've seen is around HTTPS certs preventing upstream services from forwarding requests to a downstream service. CDNs, API gateways, and even your application could all be to blame here because the issue usually involves some missing assumptions on both sides of the request. 503, service unavailable. This code usually means that a service is overloaded or temporarily unavailable. Health checks and resource utilization are the best places to start here. If you see this regularly, it could be a capacity issue. Deployments and maintenance modes are other common causes for this issue. 504, gateway timeout. This usually means that the request started timing out somewhere along the way. When you see a 504, start checking timeouts on load balancers, API gateways, and firewalls. Often it's a case of one component's timeout expiring before another component has finished processing the request. And besides these common status codes, make sure to check the docs for your CDN or cloud vendor. AWS, Cloudflare, Nginx, and others all document a list of non-standard HTTP status codes they use to provide additional context and nuance for cloud detectives. Response headers are like breadcrumbs left along the request path. They can tell us where a request has been and give us clues about any changes made along the way. CDN headers reveal where a request has been cached, how it's traveled, and whether it was served from cache or origin. If requests are misbehaving, check if they're being routed to unexpected regions, or if stale cache entries are causing issues. Application headers, like X powered by, can often be useful for pinpointing an error. Pro tip, when investigating headers, don't just look at what's there. Look for what's missing. If your application always returns X powered by Spring, but it's missing from a request that has an error, it might be the clue you need to rule out your application as a suspect. The response by itself can reveal the origin of error. Standard error pages often give away the culprit. Nginx and Apache include unique signatures in their HTML error documents, while API gateways often default to JSON responses instead. Load balancers like to take a Spartan approach to reporting errors and typically only return the status code and header. They prefer an empty body so they can spend more time serving other requests. The layout and content of an error page can be the clue that confirms the involvement of a particular error component. Building an evidence file means keeping a record of every status code, header, and response time for each problematic request. Make sure to note things that seem out of place or don't align with your mental model of how the system works. Not only does writing this down help with the current case, but over time, it builds a pattern library we can use in future investigations. Each clue adds to our case profile, helping us detect anomalies faster next time. And as you collect evidence, refer back to your architecture diagrams. See where requests might break down and try to figure out if that aligns with the evidence. Gumshoes, we've been through our toolkit. We've met the suspects and learned how to collect evidence. Now it's time to revisit our opening case. Let's dive back into the story of the phantom request, the one that would intermittently vanish, leaving a major customer frustrated and our team stumped. First step in any investigation, map the crime scene. So we've traced the request journey from user to CDN to WAF to load balancer to API gateway to Kubernetes ingress and finally to our application. 6 different places where the request could vanish, 6 suspects in our lineup. Let's review what we knew. The customer was reporting timeout errors, different users were all affected with no clear pattern, and our application logs all showed success. I think we have enough info to start forming hypotheses. So let's start with some of our usual troublemakers. First, we asked, could the requests be getting lost before they even hit our servers? DNS caching, regional routing at the CDN, or SSL misconfiguration had all led to partial site outages in the past, but the evidence didn't line up. Usually a DNS or CDN error have more of a consistent pattern and don't strike intermittently. The customer should have noticed the entire site being down, not just issues with a handful of requests. Our WAF is our next suspect because it has a reputation for unpredictability. Its rules, a mix of rate limits, black boxes, and IP block lists, make it hard to tell why it stops some requests while waving others through. However, the evidence didn't match our WAF. It usually returns a 418 status code for blocked requests. At this point, we also discovered a critical clue. Customer requests were in our application logs. Timing and user IDs lined up perfectly. The only wrinkle was that the application was reporting a 200 status code, which didn't match a 504 timeout that the customer saw. But this discrepancy pointed to a breakdown in the response journey. So looking at our evidence, a 200 in our logs, but 504 on the client, means something's giving up along the way. Since the load balancer is directly in the middle of our network stack, it's a good place to start, because if it isn't the culprit, it should help us narrow down the suspects to one of the services that comes higher or lower in the network stack. So we pulled the logs from the load balancer, and that's where we found something interesting. A handful of requests were taking just over 30 seconds to complete, around 31 or 32. But our load balancer had gotten impatient. It had a timeout set to 30 seconds. We'd found our guilty party. So now that we knew the problem, we were ready to fix it. So we increased the load balancer to timeout to 45 seconds. This gave us the application enough time to complete the longer running requests. We also had to verify that the timeout rules on the API gateway, Kubernetes ingress, and application to ensure that they matched up. It wouldn't do much for the customer if we bumped the timeout at one layer, only for the same issue to catch them and another hop along the journey. So some lessons learned. 1, documentation is critical. It would have taken us forever to discover this issue if we didn't have a request diagram to help us understand where to look. Not only that, now that we know timeouts can be an issue, updating the runbooks with the timeout settings will save us and our colleagues future headaches. A well-documented system makes these cases easier to solve and prevents similar issues from cropping up again. End-to-end visibility is key. We couldn't accuse any suspect until we had some evidence to help us understand what was going wrong. Distributed tracing, consistent logging at each layer can go a long way to helping you discover the root cause. And misconfigurations are a frequent culprit. In fact, most cloud networking bugs happen in the gaps between services. Each component was working correctly, but they weren't in sync with one another. So Gumshoes, we've come a long way. We've unpacked the tools, met the suspects, and walked step by step through a real-life case. If you remember anything from this talk, I hope you take away the following tools for your future cloud mysteries. Start with evidence, not assumptions. Gather facts first, document the observations, and let the evidence guide your investigation. Document everything. Keep your architecture diagrams current and update those runbooks after every incident. Build relationships with system owners. The cloud is too big for any one person, so get to know your infrastructure teams. Share your findings with them and learn from their expertise. And remember, every system was built by engineers. All systems are code, all code is bugs, all services have owners, and all problems are solvable. Thank you all. My name is McLoughlin, and I'm a cloud detective at CarGurus. If you're curious about what's complex or crunchy, about interfacing with the auto industry, or you just want to trade stories about solving tough technical problems, I'd love to chat with you. If you're local, I also want to give a shout out to our sister company, CarOffer. It's a fantastic place to work, and they're doing some really exciting things in the automotive space. I'm active on several social networks, which I've listed on the slides. If you like this talk, or if you have feedback, I'd love to hear from you. Post about this on your social network of choice, and please tag me. Not only do I love connecting with other engineers, but I also like to collect a little social proof for my boss. Thank you.